Hi, I'm Ahmed.
And I'm Kieran.
We're going to talk to you today about endorphins.
What you just saw is one of the most common daily occurrences in which endorphins play a functional role in your body.
However, before diving into endorphins and talking further about them, we must first talk about the endocrine system, but more specifically, endocrine control, which deals with how various glands, as well as organs, manipulate and control the levels of different hormones within your body.
Okay, so today what I want to talk about is endocrine control. And in order to talk about endocrine control, I need to talk about two major glands. First, the hypothalamus, and then the next major gland that we need is the pituitary gland. And you can see that the hypothalamus is a structure right here in the forebrain, and the pituitary dangles right beneath it. And as a member of the brain, the hypothalamus receives neural signals from the brain and from the peripheral nervous system, and it funnels those signals to the pituitary gland, which ultimately controls the other endocrine glands and our body's hormonal response to the environment.
Now that you've learned about endocrine control, it is now time to further investigate one of the major players involved directly with the synthesis and action of endorphins, the pituitary gland.
So the pituitary gland is a pea-sized gland that sits essentially right in the center of the brain. It actually is housed in a part of the skull that is known as the sella, which gives it a little bit of room to actually grow. Because the pituitary gland is such an important gland and life is really not sustainable without it, it is highly protected within the brain. And if you go up through the nose and straight back, you will hit the pituitary gland. It does lie right beneath the optic chiasm, which is the crossing of the optic nerves. The pituitary is considered the master gland by many in the body because it regulates the production of other hormones from glands located elsewhere. And those hormones include the production of thyroid hormone by the thyroid gland. It runs the adrenal glands with the production of ACTH. It produces growth hormone, which has a multitude of functions, but particularly in children regulates growth and development. It also produces prolactin, which is important in terms of lactation during pregnancy. And it regulates water and fluid balance. So usually pituitary tumors, unless they become larger than 1.5 centimeters, do not compress other brain tissue and do not cause other problems. However, when it does exceed above a 1.5 centimeter, we do worry about it extending and compressing above that area and into other tissues.
Now that you know about the extent to which the pituitary gland functions in hormonal control, as well as pituitary cancer, which leads to the development of harmful tumors, which can then in turn severely impact the functioning of the pituitary gland and lead to negative effects on hormonal levels, such as a reduction in the amount of endorphins which are produced. Now moving on, it is time to dig deeper and explore in greater detail the function of the hormone, as well as the structure of the hormone, and the various diseases and medical pathologies that are associated with endorphin levels that differ from the norm.
Let's roll! To start, let me say that the word endorphin is a combination of the words endogenous, which means produced in the body, and the word morphine, which is an opioid or narcotic used to treat moderate to severe pain. Endorphins are opioid peptides produced by the body, and they're often called the body's natural pain relievers. They're thought to be what causes an increased sense of euphoria and well-being. They are believed to be produced by the hypothalamus and pituitary gland during intense exercise, in response to physical pain, during sex, when listening to music, during laughter, and even while eating certain foods like chocolate and spicy stuff. However, endorphins can't pass through the blood-brain barrier, but a different opioid peptide called enkephalins are synthesized in the brain and could be the cause of the euphoria mentioned before. In a recent experiment, runners were given a brain scan before and after a run. Researchers found that there was an increase in opioid release in the runners' brains, and the subjects who reported the largest levels of euphoria showed the highest levels of opioid release in their brain scans. As these enkephalins are released, they attach to target nerve cells that are studded with opioid receptors. They lock into these receptors, changing the surface of the cell. It's believed that this process blocks pain and causes the sense of pleasure. Certain enzymes will then come and remove the enkephalin molecules so the nerve cell can go back to regular work. Bottom line time. Endorphins and enkephalins are in the same family. They're both opioid peptides. They are essentially the body's own euphoric drug. Doing activities like exercising, having sex, and jamming to some tunes are not only good for you physically, but mentally as well.
The origins of endorphins have been traced to the precursor pro-opiomelanocortin, or POMC, polypeptide, which is synthesized within the pituitary gland. Recent studies have produced evidence suggesting that POMC may also be produced by the immune system and, consequently, also provide a base source for endorphin production. POMC consists of a 241 amino acid chain which is cleaved by enzyme prohormone convertases action into 93 amino acid single chain polypeptide beta lipoprotein, or beta LPH. Beta LPH is cleaved via enzymes into beta melanocyte stimulating hormone and endorphins, amongst other types of hormones. Endorphins are identified as three distinct peptides termed alpha endorphins, beta endorphins, and gamma endorphins, respectively. The beta endorphins are the longest chain, comprising of 31 amino acids. This sequence corresponds to amino acids 104 to 134 in the sequence of beta LPH. The second longest chain is the gamma endorphins, consisting of a 17 amino acid chain, the same as the first 17 amino acid chain sequence of the beta endorphins. Finally, the third and shortest type of endorphins about the amino acid chain sequence are the alpha endorphins. The alpha endorphins are amino acid chains comprised of the same first 16 amino acid sequence as the beta endorphins, and consequently has the same sequence of the first 16 amino acids comprising the gamma endorphins. Thus, the sequences of beta endorphins and gamma endorphins essentially have the same sequence as the alpha endorphins that are nested within them. This molecular configuration thereby allows these endorphins to be the agonist of opioid receptors, the same receptors to which chemicals derived from opium, such as morphine, bind to for triggering physiological responses.
Now, to understand the physiological response, we must first take a look at how the ascending and descending pathway of pain takes place and what role these naturally occurring opioids play.
Imagine you had a right hand injury. What happens, and how do we feel pain? The pain signal coming from the site of injury will travel up to the brain, and this is where the perception of pain essentially is felt. The signal going up to the brain is referred to as the ascending pathway. Injuries to our body is felt in certain areas of our brain called the somatosensory cortex. The somatosensory cortex sits posterior to the central sulcus. Let's get a cross-section of the brain like so and zoom into the somatosensory cortex. The somatosensory cortex is an area where sensation is perceived. This includes pain. The somatosensory cortex has areas which correlate to different parts of our body. So for example, let's look at the left side of the somatosensory cortex. The outer region here represents the leg, hand, and face. Again, this is your right side and this is your left side of the brain. The brain continues on and joins with the brainstem, which is made up of three main components: the midbrain, pons, and medulla. These are cross sections of the brainstem. The brainstem then continues on and becomes the spinal cord. Here we are only looking at one section of the spinal cord. Let us say this section of the spinal cord is a cervical spine area. The spinal cord has nerves coming out from the anterior root and nerves coming in from the posterior root of the spinal cord. Here I am only drawing the nerves on the right side of the spinal cord. Different tracts exist within the spinal cord. One tract important in the pain pathway, or the ascending pathway, is the spinothalamic tract, made up of the lateral and anterior spinothalamic tracts. Let's go back to the right hand injury now. The right hand has an obvious injury on its palm. Within the area there are immune cells residing. When these immune cells are damaged, or should I say when any cells are damaged, including our skin cells, they start releasing cytokines, chemicals. An important one in the ascending pathway are prostaglandins, represented here as PG. Prostaglandins are produced by nearly all cells, typically as a response to inflammation. Sensory nerve fibers exist all over our body. These sensory nerve fibers will respond to prostaglandins and will carry the signal or impulse to the back of the spinal cord, or the dorsal horn of the spinal cord. This neuron is a first-order neuron. Within the dorsal horn of the spinal cord, the first-order neuron will synapse and relay this signal, this impulse, to the second neuron. This second neuron, called the second-order neuron, will cross over to the opposite side and will enter the spinothalamic tract. From here, the second order neuron will continue up, ascending through the remaining spinal cord, through the brainstem, and terminate in the thalamus of the brain. The thalamus is the relay station. In the thalamus, the second order neuron will synapse with a third order neuron. The third order neuron will carry this impulse and relay it to the region of the brain which correlates with the injured right hand. Thus, the third order neuron helps discern the area of injury, and also the cortex here is where the perception of the pain is perceived. Important to remember that this is the left side of the brain, whereas the stimuli, the initial signal, was on the right hand. Thus, sensation always is on the opposite side of the brain to where the stimuli or stimulus occurred. Another important thing to remember is a chemical released by the first order neuron to transmit or relay the signal impulse to the second order neuron. This chemical is substance P. Thus, substance P and this whole area at the dorsal horn of the spinal cord is an important area for the ascending pathway. Now, whenever there is an ascending pathway, there is a descending pathway. While the ascending pathway is responsible for transmitting the pain signal up to the brain, the descending pathway is responsible for controlling and inhibiting the ascending pathway, essentially. When not inhibited, the neurons arising from the periaqueductal gray matter will go down to the nucleus rhabdomagneus and synapse with a second neuron. This second neuron here is a serotonergic noradrenergic neuron. And this serotonergic noradrenergic neuron will travel down towards the dorsal horn of the spinal cord as well. The serotonergic noradrenergic neuron's role, in summary, is to inhibit or control the communication between the first order neuron and the second order neuron of the ascending pathway, and thus help control pain signals going up.
Descending pain modulatory neurons in the rostral ventral medial medulla and DLPT inhibit nociceptive transmission by several mechanisms: direct inhibition of projection neurons, inhibition of transmitter release from primary afferents, excitation of inhibitory interneurons, and inhibition of excitatory interneurons. Functional studies show that these modulatory systems can exert bidirectional control of pain in response to higher order factors such as fear, attention, and expectation. Opioid peptide synthesizing cells and opioid receptors are distributed throughout the pain modulating circuit. The release of endogenous opioid ligands at spinal sites can produce an analgesic effect. These substances function in part by reducing transmitter release from the dorsal horn terminals of primary afferent nociceptors. They also direct postsynaptic inhibition of central neurons that are activated by noxious stimulation. Both mu and delta opioid receptor agonists block excitatory amino acid release from primary afferents. Endogenous opioids also contribute to pain modulation by inhibiting neuropeptide release from primary afferents.
Endorphins play a crucial role in our body, and a deficiency can cause the following symptoms: chronic pain, especially in the back or the neck, chronic headaches and migraines, pain-killing medication don't seem to help, very emotionally sensitive, very low pain threshold, light touch, loud sounds, and bright lights can trigger it, tendency to tear up easily, not having fun in life, depressed, craving pleasure foods like chocolate, sugar, and wine, diagnosed with fibromyalgia. Did you know people with an endorphin deficiency will often have a GABA and serotonin deficiencies, but often not respond well to typical antidepressant medications? Biggest factors that reduce endorphin levels are chronic stress and adrenal fatigue, inadequate or ineffective sleep, poor blood sugar stability, gut microbiome dysbiosis, caffeine and alcohol consumption, GABA deficiency, spinal subluxation, and physical and emotional trauma. But there are ways to improve endorphin levels, like anti-inflammatory diet, regular sun exposure, see your chiropractor, listen to your favorite music, eat some dark chocolate, consider acupuncture, deep breathing, regular exercise, practice stretching exercises or yoga, laugh, and play. In summary, there are 3 types of endorphin peptides, which are known as alpha endorphins, beta endorphins, and GABA endorphins.
They are endogenous opioid neuropeptide hormones which are produced within the pituitary gland.
They interact with opioid receptors in the brain to reduce our bodily perception of pain and act similarly to drugs such as morphine and codeine, which are known pain-relieving compounds.
Having a lack of endorphins can cause the following conditions: chronic pain, migraines, sensitivity to light, depression, fibromyalgia, as well as a plethora of psychological abnormalities.
As you can see, endorphins play a critical role within our bodies, and without them we would be severely limited in our capacity as human beings.